Good morning, everyone. Yes, everyone, please have your seats. Thank you for joining us this morning. My name is Anca, Gurzu. I'm the Chief Europe Correspondent for Cipher News. Cipher News, is that me? Cipher News is a publication that covers the intersection of climate and technology, and we focus on the clean energy technologies we need to reach net zero. So if you've heard in the short introductory remarks about why carbon removal technologies are important, the role they can play, and we're going to also hear about why it's important to scale them up. And we thought that in this first panel sessions, it would be nice to get a bit deeper and understand what kind of technologies there are out there, how do they work, where we're at with them, and we're going to hear from different companies about those kinds of options. In a way, it's meant to set the scene for the rest, as you heard, the program for the rest of the day. So I want to now introduce all of our panelists, and we have Charlie Hendry-Smith. He's the Carbon Removal Development Manager at Veolia. We have Richard Jackson. He's a director at Standard Gas. We have Dan Deviri. He's the CEO at CarbonBlue. We have Saskia Wunderink. She's the Sustainability and Impact Lead at Skytree. And we have Olafur Gudnason. He's the Head of Policy at Carbfix. So thank you, all of you. And to note also that as part of this panel, we're also going to have some visuals we're going to see behind us to help us better understand what we're talking about. So I would like to start with you, Charlie. Tell us a little bit very briefly about Veolia, how Veolia got into the carbon removal business. And I know you're using a technology that's called enhanced rock weathering.
Yeah, thanks for that. Yeah, so hello everyone. I'm from Veolia, and yeah, we are a very large environmental services company. So we operate across waste, water, and energy. We're in 58 countries around the world, and we currently provide decarbonization solutions to our clients. And carbon removal is really that last 10% that we're looking to provide to our clients. And we've got really interested in enhanced weathering to begin with. It's been our inroad into carbon removal space because there's a lot of co-benefits to agriculture, and it's quite easy to get into. So we don't need to develop large infrastructure, and we can use existing supply chains.
Can you tell us how it works?
Yeah, so I think it's helpful just to roll back to sort of the initial carbon cycle. So if we look at how carbon cycles through the atmosphere and through the geological system, there's an aspect where there's this weathering that takes place. So there's CO2 in rainwater, and when that comes into contact with volcanic rock, then minerals are released into the natural environment, into the soils. This boosts crops. That's why volcanic soils like Indonesia are very, very fertile. And during that process, the CO2 reacts with the rock and dissolves in the soil pore water to form a bicarbonate. So it's basically going from a gas into a solid, and then that's washed into the ocean. And so it's stored in the ocean, and after 10,000 years, it then forms limestone. And we are really engineering this natural process by utilizing very, very fine rock particles and spreading them over large areas of land. So we're accelerating this process, which normally takes thousands of years, to hopefully less than 5 years.
So this is something that happens naturally, and we're trying to find ways to accelerate it. And you said, and you do that by grinding the rocks, or?
Yeah, so this is an existing practice. These rocks are mined for aggregates and construction industries, and we're using one of the lower value byproducts that they produce, which is the dust, which is produced when they grind for the larger rock particles. And we take this material and we take it, we send it for analysis. We make sure it's all within the safe, potentially toxic element limits, and we understand the nutrients within it. And at the same time, we're doing testing of the farmland to see what are the conditions within that. And we're making sure that when we apply the rock, we're going to be having a beneficial impact on the farmers' fields.
And there's also an innovation part on top of the enhanced, like you're using the enhanced rock weathering, but you're adding enzymes?
Yeah, that's right. Yeah, so one of the key challenges in the sector at the moment is like how can we really accelerate that carbon removal rate? So we are looking at how we can use crushing equipment to reduce the particle size, but it's a little bit challenging to really get it down to the size that we want at the scale that we need it. So we're exploring the use of an enzyme with a company in London where we can use existing infrastructure that farmers use to spray their crops with pesticides and fertilizers. We're using that same equipment to spray enzymes on top of the rock. So it's creating this process that accelerates the weathering rate. So yeah, this is a new area that we're looking into.
And where are you at in understanding how efficient it is?
Yes, so we are working quite closely with a number of different partners in the space. There's been a lot of established understanding about enhanced weathering, so it's been really developing a lot recently. There's work that Isometric and Pure Earth and Cascade have all been doing to understand the methodology behind the space. And this has been really important in getting us to a state where we really understand what we need to do and what's going on. And now it's a process of we've deployed the rock into the fields, and now we need to kind of wait for the weathering process to happen to see what conditions have led to the weathering rates. And in that process, we understand what's going on. But yeah, we are scaling up. But first, we're deploying into the fields at a smaller scale to understand what's going on before getting.
How long does the weathering process take?
Yeah, so naturally, it can take thousands of years. If you just take the rock straight from a quarry, it may take 20 to 30 years to fully weather. But with additional crushing, additional screening of the rock before you take it to land, and with the enzymes, we're aiming to get it to below 5 years. So we are only generating carbon credits based on what we've measured to have been removed. So we take measurements before we apply the rock, and then we take measurements every 12 months and account for all of the process emissions within that. And through that process, we're able to create a carbon credit at the end of it.
Okay. Definitely have more questions, but I do want to move on, and maybe we'll get to tackle those in the second round. That's great. Thank you. I hope I understood very well how you explained it. I hope everyone did as well.
Hopefully.
I want to turn now to Richard. Where are you, Richard? Here. Standard gas. You tell us about the technology you're using and how it's different from what we see on the market today.
Sure. So standard gas really is a pyrolysis technology. So where it differs from normal pyrolysis is in two ways. The first is the type of feedstock it can treat. So normally pyrolysis will take biomass, it will heat it up in the absence of oxygen and make a char, and then there's normally a vapor fraction and sometimes an oil fraction as well. We do that, but we can take a much broader set of feedstocks. And the reason we can do that is that we also have a petrochemical cracking process on the back of it all. And that means that you don't get the huge tar build-up that you get if you don't operate pyrolysis sort of in the optimal range of temperatures. So imagine 1 minute with a normal feedstock, it's damp, it's wet, it's got a low calorific value. You will need to obviously heat that a lot more, put a lot more energy into that to pyrolyze it than you would, say, tire crumb that's dry, very, very highly calorific. And normally, if you try and put those two things in sequence through any pyrolysis technology, it will be the wrong conditions for one of them, and you will start to cake up your machine. And then after a week of doing that, you will have gum everywhere or tars everywhere, and that will make it uneconomic because you have to take it apart, clean it out. And that's been the problem for pyrolysis for probably the last 40, 50 years. So we've solved that by keeping that gas moving, keeping it very, very hot, and then actually taking it even higher in temperature than normal, up to about 1200 degrees C. And that really cracks those long chain molecules down to something that doesn't then cake up the machine, as it were.
Richard, can we take it? I see there's a nice visual on the screens that's showing right now. And can we take it one step back and maybe also explain to the audience pyrolysis, what it means, and break it down, and maybe walk us through that process, from.
Sure. So I think the easiest way to explain pyrolysis and picture it is if you put something in your oven, although there's oxygen in your oven, if you left a lot of stuff in your oven at a very, very high temperature and came back to it, you'd have a black char at the end of it. Right? That is the first thing that we make is a char. right? Whether that is a biochar, if everything was biogenic that went in, so everything was a tree or cardboard or paper, then you'd have biochar. But if you start putting in just mixed waste, then that black substance, some element of it is fossil, some of that element of that came from plastic, and so we just call it a refuse-derived char. The majority of that char is actually biogenic carbon. The second thing that happens in your oven is you'll notice the sides of the oven are full of tar. So that is the gas phase that is then hit something and sort of condensed. So what all pyrolysis produces is a vapor fraction or sort of energy-rich gas that you can use, whether you use it to generate electricity or you can give it, well, our plans are to give it to chemical parks where it will replace natural gas. So it will mean they stop burning fossil fuel and they burn a fuel that's derived from waste. And then the second thing that we can do is take that char and sequester it. And obviously that's where the carbon removal is. So it has two actual benefits that are independent of each other.
And where do you store it, the char?
So the plan at the moment, the problem we have with char that isn't biochar is the regulation needs to catch up with where we're at. So at the moment, the plan is to landfill it. Now, the science says that's actually the best place for char. It's incredibly stable for tens of thousands of years in landfill, and so putting it in landfill is a great place for the environment. It's not so great place for our business because it costs money to do that. We'd like to see it go into materials, maybe into roads, concrete, into even things like bricks. I mean, people say, well, you can't put it in bricks because you have to bake a brick and then it will burn. But there are ways of getting char into things like tiles, bricks, building materials. But again, that's a regulatory thing we have to get over the next coming years.
So the main thing behind this technology is also the fact that you can take general waste, not just biomass that we've seen.
That's right. We need to sort it a little, so you don't want metals in there. You want the tin cans taken out. You don't want PVC, so certain high chlorine content waste, because that will form hydrochloric acid and rot everything. But I think general incinerators have the exact same requirements. So it's very applicable across the world for a number of wastes. And one of the other things we're looking at is, it's not very sexy, but sewage sludges, so treating, sort of helping the water industry treat those effluents, because the problem they're having is currently land spread them, and the microplastics and the PFAs, these sort of molecules like that you find on Teflon frying pans, they get through that process and they just accumulate in the environment. So there's a lot of move now to try and heat treat those because we need to get rid of those, and pyrolysis certainly destroys those.
Sounds great. And we'll come back to where you are in the business side of it later. I want to turn to Dan. CarbonBlue, just by the name, I'm understanding that it has to do with water. You're trying to remove CO2 from water. Tell us about it.
That's true. So the premise of the company is that, and that's a fun fact, that actually 98% of the carbon dioxide in the carbon cycle, in the natural carbon cycle, is in water. And water has a much larger concentration of carbon dioxide in the air. So by targeting water and capturing carbon dioxide from water, we can get removal facilities that are relatively small and cheap. And doing that, what we're trying to do is to match industries that are using water, leveraging existing infrastructure for water withdrawal and driving costs down, with companies and industries that are interested in this carbon dioxide, whether it is chemical industries that requires it as a feedstock, or storage companies that want to store it down and generate carbon removals.
Can you give us an example of how it works, like of the process?
Of course. So the process comprised of 2 steps. In the first step, we just pump the water through a proprietary reactor that we developed that can mineralize the carbon dioxide in the water into a solid form that is easily separable by filtration by very, very cheap and simple filtration. It's a millimeter-sized spheres made of carbonate mineral that we can collect. Then we can transport this carbonate mineral into the place that needs the carbon dioxide. Sometimes it's the same place where we produced it, but we can transport it over long distances relatively. And then with a secondary process that is also a proprietary process that we developed together with an academic research institute, we liberate the carbon dioxide and regenerate the cheap and safe minerals that we use to mineralize it in the first place, which is shipped back into the mineralization facility to capture more carbon dioxide from water.
Okay, so that part is also interesting. So tell us again what happens to the water after you took the CO2 out? How do you stimulate then to?
So we don't require any supply chains. The minerals that we use are recirculated and completely regenerated in the process. So we do not add to the water anything. So basically, we do not change the chemistry of the water up to one point, which is take out the carbon dioxide. Now, carbon dioxide is an acidic gas. So by taking it out of the water, we actually make the water more alkaline, which can be better for the environment because of ocean acidification. But we also, by removing the carbon dioxide, we make the water less prone to limescale, which is something very harmful to any industry using water. This is the same scaling that appears in cattle. And we can help with that as well.
And how do you measure the results? How do you know how much CO2 you took out?
So it's a very good question. The problem, of course, is to understand how much carbon dioxide, once we removed the carbon dioxide from the water, we formed like some kind of a sponge that the water reabsorb back the carbon dioxide from the atmosphere. And that's the tricky part to measure, because how much carbon dioxide we remove from the water, that's simple. We can measure it as a metric output from our facility. But measuring the drawdown of atmospheric carbon dioxide, this is something that we work with other companies in this field and NGOs made of scientists, of oceanographers, to construct the methodology how to measure that. Basically, what we do is we measure the water chemistry, the CO2 content and the temperature and water flows really close to the discharge point of the water, which we still can do it because that's before the water got mixed up with all the ambient water. And then we feed this data into a computer simulation that can predict the flows of the water and the interaction of the water with the atmosphere, and predict the drawdown or estimate the drawdown of carbon dioxide. So basically, it is a simulation, a computer simulation model that is based on real-time data that we collect close to the discharge point.
Okay, so you have a method, but there's still a methodology that's being developed to fully grasp. Yes. Okay, that's great. Thank you for that. We'll come back again to ask you where you are also in deployment and all of this. I want to turn to Saskia now. Skytree. Cannot tell from the name necessarily at first glance what you do, but I know it's direct air capture and technology. Yes. Please walk us through what you do.
Certainly. So Skytree is a direct air capture company, which basically is the technology of filtering CO2 molecules from the atmosphere. We are a tech provider. We call ourselves technology providers because we build machines that are able to do this process of capturing your CO2 molecules from the air. We exist for quite a long time already. We were founded in 2014 as a spin-off from the European Space Agency. Our technology was developed there in order to filter CO2 molecules from the indoor air of the space station. Now, of course, it took quite some time to transfer that tech to working conditions on Earth, which were quite different from those in space. But we have developed quite a lot, and now I can say we are quite far. We can maybe go through that later as well. Our technology works by grabbing the air. With filters, it goes through our units, where there is a capture material which specifically grasps the CO2 molecules. So those are specifically grasped from the air. Then in a second step, the capture material is heated up to release the CO2 molecules. And those are collected in a subsystem, which I hope you can see over there. Yes, great. So these are the 3 steps of our system. So it's first, it's the air flows through. Second is heating up to release CO2 molecules. And third is collecting the CO2 molecules. Then for creating negative emissions or actually removing CO2 molecules permanently for the atmosphere, we need a partner. We need a storage partner. So we provide you with the CO2 from the air. The storage partner provides us with a methodology in order to permanently remove these CO2 molecules from the atmosphere. And that's really where you create these negative emissions. And that's really how we can set up our technology in order to help climate change.
So we're definitely going to get to the storage part as well,
yes.
Obviously an essential element. But from all the technologies that we've heard so far, yours is more like the most engineered solution, right, from all of them?
Yes. Like I said before, we really call ourselves tech providers. I hope that there is also a nice image of our machines in the slides as well. You can think of our units as really, really large Lego blocks. We make decentralized direct air capture. So we build units that can provide you with CO2 molecules on site. So wherever you need them, whether that's you're building a facility that stores CO2 molecules in a building material, or you're building a facility that can store CO2 molecules underground, we can provide you with the technology to actually capture the CO2 molecules that you need on site. So that's really, yeah.
Yeah, no, I'm just thinking because probably for the audience, when you hear direct air capture, probably the other company that comes to mind is Climeworks, right, in this space. So how are you, I am understanding based on what you're saying that you're different, obviously, in the sense that you provide smaller machines and you're more focused on the tech.
So I think Climeworks really develops sites, and we really develop out-of-the-box technology. So we can go to you with a machine, we put it on the truck, we deliver it to you, and then you have full control over your CO2 supply. I think that that's really a key difference between us. We both grab CO2 molecules from the atmosphere, yes, but we build decentralized direct air capture. And not only does the client then have control over their CO2 supply, but you can also quite easily scale this. So we can provide you with 1 unit, we can also provide you with 10 units, depending on the amount of CO2 that you aim to use.
Okay, no, that's very clear, the different approach. And the other question that obviously comes to mind is, what kind of energy source are you using for your machines and how energy intensive are they?
Yes, of course. So energy consumption is a key factor of direct air capture. We are, for example, looking into actually sites where you can use waste heat as an energy source for our units. Not only because it helps with the cost, but also because that helps with your climate impact. Using renewable energies or waste heat is really essential for your climate impacts. Yeah.
So I guess the difference is that when you tell your customer, here's our machine, you also don't care what kind of energy they use to run it, right? Like it's up to them to decide what energy source they use.
Well, if you're creating negative emissions, you make sure that you're using good energy, because otherwise you cannot generate any credits. So
that's right. That makes sense. Great. Thank you. So we spoke about storage. Now it's time to learn a little bit more about how it works. Olafur, Carbfix. How do you store the CO2? And who would you naturally partner here from what you've heard?
Well, Carbfix was established almost 20 years ago as an international research collaboration to investigate whether we could use, well, some of it has been touched upon already, the property of volcanic rock to store CO2 through the creation of carbonate minerals. And the volcanic rocks in Iceland, the basalts in Iceland, are kind of a very, very good type of rock for that to happen. So we have now, in 2012, we started the first injections of dissolved CO2 in water into the Icelandic bedrock to test whether the CO2 would react with the rock to create these carbonate minerals. And it turned out that it happened quite quickly. So within a few weeks and months already, a substantial amount of the CO2 that went into the rock, several hundred meters underground, had mineralized into calcite. And within 2 years, over 95% of the CO2 has mineralized. And I have a sample of what really the result is. The white spots in this basaltic rock sample are former CO2 that has turned into stone deep in the ground. And what used to be there before was just empty space, which is what allows the CO2 to flow through the rock. And the great news is that the storage capacity of these rocks are enormous. In theory, Iceland alone could store all of the CO2 emissions of the planet. But for many reasons, that's neither feasible nor sensible nor practical. That's not our goal. But it just gives you a sense of the context that the availability of storage space is vast. It is quite a cost-competitive method, safe method. We just create carbonated water. There's nothing added to the water. And we have now, since 2012, mineralized approximately 100,000 tons of CO2 using this method. That has been thoroughly proven. We just recently, in collaboration with Climeworks, got our mineralization and removals, direct air capture as well, certified under the Puro standard just a few weeks ago. So that was a major milestone for us. And we have bigger plans for megaton scale project already underway in Iceland as well. But basalts are found in many places around the world. So we are looking at scaling internationally as well.
Okay, so let's talk about that, because you started touching a little bit on the business side and where you are. So we can go backwards and get to that. But you know, you mention Iceland, right? Obviously, it also sounds you need a specific type of rock for this to work at the level you would want it to work.
Yeah.
So where else in the world do we have these kinds of rocks?
Basalts are found at approximately 5% of the landmass on the planet and more than half of the ocean floor. So it's one of the most common rock types in the world. But there are some concentrated areas. In the US, it's largely in the Pacific Northwest, the so-called Columbia River basalts. We have basalts in Europe as well. We actually have a map on our website where you can see a high-level image or map of where basalts are known to be found. But they are not necessarily applicable or feasible to work with, but worth investigating. So you have basalts in India, in Kenya, in Ireland. I could go on and on. It's found all around the globe.
All around the globe.
Yeah.
And tell us a little bit more about future, because everyone, well, not everyone, but people in the field know that you work with Climeworks, and that's usually the kind of collaboration that comes to the foreground when we talk about this. Where else are you looking, and what other kinds of partners? I mean, just from this conversation, to test ourselves to make sure we understood correctly the carbon removal methods. Naturally, a partner could be Dan, right? The CO2 that he captures, or clients of Skytree, they could come to you, right?
Anyone that has CO2 that they have captured and can get it to us, or we can get to them.
Yeah.
So that is the key thing, to link the captured CO2 with the storage. So we are a storage provider for anyone that has CO2 that they need to get rid of permanently. And I forgot to mention, of course, this rock is not going to leak anywhere or disappear. It's going to stay there.
And how do we know that? I know we say it's scientifically proven, but how do we know that it's going to stay for millennia?
That's the science that just tells you. I don't know what to tell you. Let's have a look and see what happens.
We'll talk in a millennia. Yeah, okay.
No, but as for partners, I mean, direct air capture companies are one. The other main source of CO2 currently for us is the geothermal power plants, a couple of them in Iceland. They do emit some CO2. It's easily captured. So that was actually our first source of CO2, captured from geothermal power plant. A major target for us is also emitters that are like European emitters or elsewhere so point source capture from industrial emissions. So for emission reductions, especially in Europe with the ETS system, they have a huge financial incentive to capture their CO2, store it, and at a permitted site, then they are rewarded under the ETS system. And we are an economic alternative for these industries to get rid of their emissions.
So your options for partners is broader.
Broad.
But what are some of the challenges you're facing? And then I would like to get everyone's thoughts on the challenges as well.
I think at a high level for storage, this is a new value chain, and I mentioned it briefly before, the connection of the captured CO2 with the storage sites. I think we will manage the capture, we will manage the storage, but it is the link between the transport of the CO2 from the captured site to the storage site, and they cannot always be next to each other, which is of course best, and that's what we have in Iceland, but you have hundreds or thousands of emitters throughout Europe that are going to capture their CO2, and they need to get it to a storage site. So transport is a key part of the value chain where a lot of work needs to be done, and policy is focusing on this, fortunately. I also feel from our perspective as a country that is going to store CO2 imported from other countries, that is a kind of a mental thing to get past, I guess, because it's not necessarily acceptable to everyone that one country is receiving CO2 captured from other countries. Host countries or storage countries are not rewarded under national greenhouse gas bookkeeping, which makes perfect sense under the current framework, but it's not necessarily obvious to everyone in the general public that so I don't have the solution to that, but it's a thing I think we need to keep in mind to kind of normalize the global or international element of these solutions. And in particular, then, if we go to Carbfix in particular, also just awareness is we are the only company in the world operating this type of storage commercially. So we need to increase awareness on it. I will take, for example, the EU mission now to map the storage potential of Europe, that we feel it's important that this method should be included in that mapping and not overlooked. So, yeah, if anyone in the room is involved with that, I would encourage them to keep basalt in mind when this mapping exercise starts, because
that's the rock we need
for this type of storage. For this type of storage that is quite economical and proven and safe.
No, that's great. Thanks for that. And I like your point also on the public awareness, and I think that's something that might be relevant for the whole panel if we have time to discuss at the end. But to look at the business side, Richard, now we're going backwards. Where are you in deploying this back to pyrolysis, and where are we in deploying? I know you're ready to commercialize it, right?
That's right. So I think over the last 4 or 5 years, we've seen a huge increase of interest in this type of technology, and the ease of which we've achieved funding is really a sea change. In 2019, it was incredibly hard to raise money. And then over the last, I would say, 18 months, that's got easier and easier. And part of that is becoming a more mature company and having more things worked out. But I think we've got to understand here the wave of sort of interest in this as a new sector, as something that people want to support. Microsoft itself is doing a lot of work in this area. It attracts money. So I'm not saying it's easy, but we are certainly now fully financed to commercialize that plant. And so what does that involve? That's just the harder bit now is not so much getting the finance to be able to do it. It's getting the regulatory things worked out, getting the permits on things that people haven't seen before. The level of comfort that I think every country needs for these big, what are basically industrial installations, is quite difficult if they're new. And I think
where's the resistance? Because you said they need to reach a certain level of comfort.
So I think things like it doesn't fit into a box. So although we for instance, we're not an incinerator, so we don't come within the rules of an incinerator. If you were an incinerator, it would take 5 years to get planning for that, and it wouldn't be certain. So luckily, we've avoided that one, and rightfully so. But there are other things like that where you have to convince the regulator you're not to be bucketed in with, for instance, that char. It is not a toxic waste. It doesn't need to be put into a barrel and buried into concrete or something like that, right? It's not that dangerous.
But
getting the level of confidence around that and the science around that, it's not so much that's difficult. It's just the regulator doesn't even know what questions to ask because they haven't seen it before.
Yeah, it's just the example you gave about it's not toxic. It sounds like you've given this explanation before to others because there might be a bit of like.
I think the biggest problem is it's not always the same stuff, right? So waste, you put waste in at the front end. Guess what? Molecularly or atomically, you get out what you put in.
Yeah.
So, but you can't tell anyone. This is exactly what it's going to be because it depends what goes in. And so that uncertainty is then from a regulator point of view taken as, whoa, well, if you can't tell me what's in there, this is a big problem. But of course, as with most things, you set boundaries, you make sure that the worst case scenario is still totally fine, and then you proceed on that basis. But it takes data, it takes time to convince people to do that.
Okay, so in your case, we're clear on the tech, we know it works, we're building it, we're using it. It's more on the regulatory side, which actually is some regulatory things will be discussed later also in this conference. What are the challenges on your side, Saskia? You did mention that there is growth also, so where are you also on the business side?
Yes. So we are actually making 2 units at the moment. We have a relatively smaller scale one, which can produce 20 kilograms of CO2 a day, and we're building a larger one, which produces about 350 tons of CO2 a year. Now, the small scale one is fully developed. We are selling it. It's already working at a couple of installation sites, one of which is in the Netherlands, where it is used to enhance plant growth with the CO2 that we produce, and it's already working there, fully operational. The larger scale unit, it is planned for Q4 this year. So I would say it's going pretty well, and it's really great to see the development that we've had over the last couple of years. It's going quite fast. Challenges, I would say, it's still with the energy consumption. So actually, this is really a focus point for Skytree to work at. We really see that it comes down to the capture material that you use, and there is just a lot of room for improvement there, which is also why we are now partnering with our capture material supplier in order to develop new material, which is going to be a lot more efficient, which brings down your energy consumption by quite a margin, and then also brings down, of course, your cost for CO2 production. So
it's innovation basically needed to what kind of clients, what kind of industries, companies are interested, like what profiles do they have that are interested in working with you?
Yes, so right now we are going for CO2 utilization as well as CO2 removal. Like I said, we are the tech provider, so we provide our technology, and then the CO2 can be used either by somebody who wants to have it on site for direct use, or somebody who wants to store it and remove the CO2 from the atmosphere permanently. In terms of utilization of CO2, like I just said, it is used quite a lot in greenhouses. So this is an area where we can deploy our technology directly and basically replace the current fossil fuel-based CO2 that's used in greenhouses right now with circular CO2. So that's an example of utilization. And then for storage, yes, you're really looking into these storage partners where the CO2 is mineralized and removed permanently from the atmosphere.
Yeah, so it sounds like everyone here is like different pieces of the puzzle in a way for different removal options. And I can imagine that you make smaller machines, and I can see that would work better for companies that use for utilization, that use CO2 for utilizations, because they're smaller. You probably don't need that
It depends. So for the smaller ones, for example, we look at vertical farms because they don't need as much volume of CO2. And for the larger units, you're really looking into more these industrial uses of CO2 or larger volumes for the storage that you need. That you need there. One other example that is very, very interesting is that there's, of course, also a lot of CCS infrastructure being built right now. And so why not use our technology to enhance the amount of carbon that you can then store with the CCS infrastructure and add your negative emissions to the storage that's already been done.
Great.
Yeah.
Thank you. I want to jump to Dan. I don't know how much time we have, but I also wanted to ask you. I know how much time we have, but I'm saying
I gave it away.
I know. You gave it away. But I wanted to ask you also where you are today in the deployment and more out of an anecdotal perspective, how you got into this business. If you can tell us in because you're the CEO of the company, very quickly, and what challenges you're facing.
So I mentioned before that we are matching sources of CO2, industries using water and industries consuming carbon dioxide. So we are now developing our pilot facility with an industry that does both. With a desalination plant in Israel, it is going to be 400 tons per year facility, operational by Q1 2025. It's a brackish desalination facility, which means that it does not desalinate seawater, but less salty water, which so far as I know, there are no technologies to remove it from brackish water because it is not salty enough, and we demonstrate here a unique ability of our technology and core benefits that we generate to the desalination facility. So that kind of wrapping up all of our strong points of our technology, and this is our go-to-market strategy. Hopefully, we will expand to more and more desalination facilities. As for your second question, how did I got to climate tech? I actually completed my PhD in theoretical physics 3 years ago, and I looked for jobs that are intellectually meaningful, intellectually challenging, and impactful. And as a theoretician, there were no jobs that I was a good fit for. So I decided to try and create my own job. And climate tech was a perfect match because whatever we develop now, and that's true for everyone in this room, this decade would shape how humanity lives in the next decade. So that was very exciting. And I decided to focus on that. For 6 months, I studied every paper of CDR I could lay my hands on and came up with what we're doing now.
Wow, so you're like an expert in all this tech we heard?
Not as much as...
not as
much. Yeah, just one panelist, yeah. No, that's great. It's also very inspirational, so thanks for that. Charlie, you want to return to, we started with you, we want to end with you. Where are you today? You explained how it works. You explained that it's good for the fields and agriculture. You explained how you do it. Where are we today in knowing that it works?
Yeah, so when we started about 2 years ago, there really wasn't a methodology out there, really, that described everything that you needed to do for enhanced weathering. And now we're at a point where we do actually have that with the work Isometric has done, really setting out exactly what you need to do to generate high-quality carbon credits from this process. And as well as that, there's Cascade Climate, which is an NGO working in this space. So they've spoken with 40 different academic institutes that are independent, and they've provided their input into the science behind this process. So it's really been a learning curve, and it's great to have that support from all of these academics and this registry services to give us an understanding about the science behind this process. And so we've established ourselves, built the systems and procedures, and now we're scaling up. The challenges really that we see are that there is so much variability within the fields, different soil types, different crops, different climates, different rocks. All of that interacts, and that all impacts the weathering rate. So we combat that uncertainty by doing lots of measurements. So we measure every hectare, and we test a whole suite of different analyses. So we're trying to do direct measurement, a lot of direct measurement right now, and we're building that understanding about what these different factors, how that influences the weathering rate. And so over time, we can slowly reduce the amount of sampling that we need to do, which will bring the costs down.
So are the costs high?
So they're comparable. So there was Lithos Carbon. They recently sold $57 million worth of carbon credits from enhanced weathering to Frontier. And that was at a per ton price of around $400. And that's currently where the market price is at the moment. And we're seeing this coming down quite quickly as we're transitioning to a more of a model-based approach in the next 4 to 5 years as we get all this data generated on the process. But we're exploring other innovations as well. So typically with enhanced weathering, it's in agriculture, between 20 and 40 tons per hectare of material deployed. We're looking in restoration type environments, so former mines or construction projects where you're actually creating a deeper soil profile. And so we can put more basalt into that. So it's bigger economies of scale. So that increased density combined with the increased rate from the enzymes, we're hoping to really bring those costs down.
So there's, a lot of ideas, and we're testing to see how they all work. And I can see that we're out of time. But I would like just to really finish one word. If you can all think of one word that you think is either a challenge or something hopeful you're thinking about for your tech and the company you're representing, what's one word for the future that's on your mind?
Innovation.
Okay.
Buzzword.
Partnerships.
Partnerships.
Volume of CO2.
What is it?
Volume. We need a
volume. Yes.
Regulation.
I knew you were going to say regulation. Yeah.
I'll second partnerships.
Partnerships.
But many come to mind. Yeah.
That's great. So hopefully that sums up a little bit what we've heard today, and we've heard that there are a lot of options out there at different phases, let's say, in their development and in their deployment. I think innovation obviously was a key theme, and cost as well. Thank you very much. I don't want to go too much over the time. In 5 minutes, there's another panel that's starting that's going to look at ways to verify and measure CO2 removal. So thank you to all our panelists for being here, and to you as well.